separating the hot and neutral conductors using a double-pole single-throw, abbreviated DPST, toggle switch is an unsafe and incorrect practice. Firstly, there isn't an electrical safety hazard. When the switch is open, the motor and receptacle are completely disconnected from the power source. However, the hot conductor remains connected to the switch, creating an electrical hazard if the switch is accidentally turned on while the device is being handled or serviced. Secondly, there is a code violation. The National Electrical Code, abbreviated NEC, requires that the hot and neutral conductors be connected through a fuse disconnect or circuit breaker to provide overcurrent protection and prevent electrical shocks. Thirdly, there is reduced motor performance. Disconnecting the neutral conductor can cause the motor to operate at a reduced voltage, potentially affecting its efficiency and reducing its lifespan. The hot and neutral conductors should be connected through a fuse disconnect or circuit breaker and then to the motor and receptacle. This ensures proper overcurrent protection and maintains the correct voltage for the motor operation. If you encounter this type of installation, it should be corrected immediately for safety reasons. It is recommended to contact a qualified electrician to inspect and rewire the device according to code requirements. It is also recommended to stay up to date with the latest electrical codes and best practices to ensure safety and compliance. Attending workshops, seminars, or taking online courses can help you keep your knowledge current. The National Electrical Code, abbreviated NEC, is a regionally adoptable standard for the safe installation of electrical wiring and equipment in the United States. It is part of the National Fire Code series published by the National Fire Protection Association, abbreviated NFPA. While not itself a law, NEC is typically enacted into law at the state and local levels. The NEC is updated every 3 years. The NEC covers electrical conductors, equipment, and raceways, signaling and communications conductors, equipment, and raceways, and optical fiber cables and raceways installed in buildings, structures, and other premises, including yards, carnival, parking, and other lots, and industrial substations. The NEC does not cover the following installations in ships, watercraft other than floating buildings, railway rolling stock, aircraft, or automotive vehicles. It also does not cover installations underground in mines or self-propelled mobile surface mining machinery and its attendant electrical trailing cable. It also does not cover installations of railways for generation, transformation, transmission, or distribution of power used exclusively for operation of rolling stock or installations of communication equipment under the exclusive control of communication utilities located at doors or in building spaces used exclusively for such installations. The NEC is organized into chapters, articles, and sections. Chapter 1 contains general requirements. Chapters 2 through 4 cover wiring and protection, wiring methods and materials, and equipment for general use. Chapters 5, 6, and 7 supplement or modify the general rules and cover special occupancies, special equipment, and special conditions. Chapter 8 covers communications systems. Chapter 9 contains tables and examples. The NEC is constantly evolving to keep pace with new technologies and safety concerns. Some of the key changes in recent editions of the NEC include requirements for arc fault circuit interrupters, abbreviated FSIs, ground fault circuit interrupters, abbreviated GFCIs, surge protection devices, abbreviated SPD, and energy storage systems, abbreviated ESS. Arc fault circuit interrupters, abbreviated FSIs, are designed to protect against fires caused by arcing faults. Arcing faults can occur when damaged or deteriorated wiring creates an unintended electrical path to ground. Ground fault circuit interrupters, abbreviated GFCIs, are designed to protect against electrical shock. Ground faults can occur when current leaks from a circuit to ground. Surge protection devices, abbreviated SPD, are designed to protect against voltage surges. Voltage surges can damage electronic equipment. Energy storage systems, abbreviated ESS, are designed to store electrical energy for later use. Energy storage systems are becoming increasingly common as the use of renewable energy sources grows. The NEC is an essential resource for electricians, electrical contractors, and other professionals involved in the electrical industry. It provides the information needed to ensure that electrical installations are safe and compliant with the law. In addition to the NEC, there are other electrical codes and standards that may be applicable to a particular installation. These codes and standards may be developed by state and local governments, as well as by organizations such as the Institute of Electrical and Electronics Engineers, abbreviated IEE, and the American National Standards Institute, abbreviated ANSI. It is important to be familiar with all of the applicable electrical codes and standards before beginning any electrical work. Electrical work can be dangerous, so it is important to take all necessary precautions to protect yourself and others. Some of the basic safety precautions that should be followed when working with electricity include always turning off the power before working on any electrical equipment, using insulated tools and equipment, wearing appropriate personal protective equipment, abbreviated PPE, such as safety glasses and gloves, never working on electrical equipment in wet conditions. And, if you are not qualified to do electrical work, then you should hire a qualified electrician. The information provided in this narration is for informational purposes only and should not be considered as professional advice. Always consult with a qualified electrician or other professional before making any decisions about electrical work. A fuse disconnect is a type of electrical disconnect switch that contains a fuse. The fuse is designed to protect the circuit from overcurrents. If an overcurrent occurs, the fuse will blow, interrupting the flow of electricity and preventing damage to the equipment. Fuse disconnects are typically used in applications where it is important to protect the circuit from overcurrents, such as in motor circuits, heating circuits, and lighting circuits. A circuit breaker is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit. Its basic function is to interrupt current flow after a fault is detected. Unlike a fuse, which operates once and then must be replaced, a circuit breaker can be reset either manually or automatically to resume normal operation. Circuit breakers are made in varying sizes, from small devices that protect individual household appliances up to large switchgear designed to protect high-voltage circuits feeding an entire city. Circuit breakers are an essential part of any electrical system and are used to protect people and equipment from electrical hazards. There are several different types of circuit breakers, each designed for a specific application. Some of the most common types of circuit breakers include thermal circuit breakers, magnetic circuit breakers, and solid-state circuit breakers. Thermal circuit breakers use a bimetallic strip to sense overcurrents. When an overcurrent occurs, the bimetallic strip heats up and bends, tripping the breaker. Magnetic circuit breakers use an electromagnet to sense overcurrents. When an overcurrent occurs, the electromagnet pulls on a trip bar, tripping the breaker. Solid-state circuit breakers use electronic components to sense overcurrents. When an overcurrent occurs, the electronic components trip the breaker. Circuit breakers are rated in amps, which is the amount of current that the breaker can safely carry. Circuit breakers are also rated in volts, which is the voltage that the breaker can safely interrupt. When selecting a circuit breaker, it is important to choose a breaker that is rated for the correct amperage and voltage for the circuit that it will be protecting. Circuit breakers should be installed by a qualified electrician. The electrician will ensure that the breaker is properly sized and installed and that the circuit is properly wired. Circuit breakers should be inspected regularly to ensure that they are in good working order. If a circuit breaker trips frequently, it may be a sign that there is a problem with the circuit. If you suspect that there is a problem with your electrical system, you should contact a qualified electrician. A receptacle is an electrical outlet that provides a convenient way to connect electrical devices to a power source. Receptacles are typically installed in walls, floors, and ceilings, and they are used to power a wide variety of electrical devices, such as lamps, appliances, and tools. Receptacles are available in a variety of sizes and shapes, and they are rated for different voltages and amperages. The most common type of receptacle in North America is the 120 volts, 15 amps receptacle. This type of receptacle is used to power most household appliances and tools. Receptacles are also available in 240 volts versions, which are used to power larger appliances such as electric stoves, dryers, and air conditioners. Receptacles are typically wired with 3 wires: a hot wire, a neutral wire, and a ground wire. The hot wire carries the electricity from the power source to the receptacle. The neutral wire returns the electricity to the power source. The ground wire provides a path for electricity to flow in the event of a fault. Receptacle should be installed by a qualified electrician. The electrician will ensure that the receptacle is properly wired and that the circuit is properly grounded. Receptacles should be inspected regularly to ensure that they are in good working order. If a receptacle is damaged or not working properly, it should be replaced by a qualified electrician. When using receptacles, it is important to follow some basic safety precautions. Firstly, never overload a receptacle. Overloading a receptacle can cause the wires to overheat and start a fire. Secondly, never use a damaged or frayed power cord. A damaged or frayed power cord can cause an electrical shock or fire. Thirdly, never use a receptacle in a wet location. Using a receptacle in a wet location can cause an electrical shock. Fourthly, always unplug electrical devices when they are not in use. Unplugging electrical devices when they are not in use can save energy and prevent electrical shocks. Lastly, if you are not sure how to use a receptacle safely, consult a qualified electrician. A motor is an electrical machine that converts electrical energy into mechanical energy. Motors are used in a wide variety of applications, such as powering pumps, fans, compressors, and machine tools. Motors are available in a variety of sizes and types, and they are rated for different voltages and amperages. The most common type of motor is the alternating current, abbreviated AC, motor. AC motors are powered by alternating current electricity, which is the type of electricity that is typically used in homes and businesses. AC motors are available in 2 main types: induction motors and synchronous motors. Induction motors are the most common type of AC motor. Induction motors use electromagnetic induction to convert electrical energy into mechanical energy. Synchronous motors are less common than induction motors. Synchronous motors use a rotating magnetic field to convert electrical energy into mechanical energy. Motors are typically wired with 3 wires: a hot wire, a neutral wire, and a ground wire. The hot wire carries the electricity from the power source to the motor. The neutral wire returns the electricity to the power source. The ground wire provides a path for electricity to flow in the event of a fault. Motors should be installed by a qualified electrician. The electrician will ensure that the motor is properly wired and that the circuit is properly grounded. Motors should be inspected regularly to ensure that they are in good working order. If a motor is damaged or not working properly, it should be repaired or replaced by a qualified electrician. When using motors, it is important to follow some basic safety precautions. Firstly, never overload a motor. Overloading a motor can cause it to overheat and burn out. Secondly, never use a motor in a wet location. Using a motor in a wet location can cause an electrical shock. Thirdly, always disconnect the power to the motor before working on it. Disconnecting the power to the motor before working on it can prevent electrical shocks. Fourthly, if you are not sure how to use a motor safely, consult a qualified electrician. The double-pole single-throw, abbreviated DPST, switch is a type of electrical switch that has 2 poles and 1 throw. This means that the switch can control 2 separate circuits simultaneously. When the switch is in the on position, both circuits are closed and current can flow through them. When the switch is in the off position, both circuits are open and current cannot flow through them. DPST switches are commonly used in applications where it is necessary to control 2 separate circuits with a single switch. For example, a DPST switch might be used to control the power to 2 separate lights or to control the power to a motor and a light. DPST switches are available in a variety of sizes and shapes, and they are rated for different voltages and amperages. When selecting a DPST switch, it is important to choose a switch that is rated for the correct voltage and amperage for the circuits that it will be controlling. DPST switches should be installed by a qualified electrician. The electrician will ensure that the switch is properly wired and that the circuits are properly protected. When using DPST switches, it is important to follow some basic safety precautions. Firstly, never overload a DPST switch. Overloading a DPST switch can cause it to overheat and burn out. Secondly, never use a DPST switch in a wet location. Using a DPST switch in a wet location can cause an electrical shock. Thirdly, always disconnect the power to the circuits before working on a DPST switch. Disconnecting the power to the circuits before working on a DPST switch can prevent electrical shocks. Fourthly, if you are not sure how to use a DPST switch safely, consult a qualified electrician. Electrical safety is a critical aspect of working with electrical systems and equipment. It involves taking precautions to protect oneself and others from electrical hazards such as electric shock, electrocution, burns, and fires. Here are some key principles and practices for electrical safety. Firstly, de-energize circuits. Always turn off the power at the circuit breaker or main disconnect switch before working on any electrical circuit or equipment. Verify that the circuit is de-energized using a voltage tester before touching any wires or components. Secondly, use lockout-tagout procedures. Implement lockout-tagout procedures to prevent accidental energization of equipment during maintenance or repair. This involves placing a lock and tag on the disconnecting device to indicate that the equipment is out of service and should not be turned on. Thirdly, wear personal protective equipment. Wear appropriate personal protective equipment, abbreviated PPE, such as insulated gloves, safety glasses, and arc-rated clothing when working with electrical equipment. This will help protect you from electric shock, burns, and other injuries. Fourthly, use insulated tools. Use insulated tools with non-conductive handles when working on electrical circuits or equipment. This will help prevent electric shock if you accidentally come into contact with a live wire. Fifthly, maintain a safe working distance. Maintain a safe working distance from energized electrical equipment. This distance will vary depending on the voltage of the equipment. Consult the National Electrical Code, abbreviated NEC, or other applicable standards for specific requirements. Sixthly, avoid working in wet conditions. Avoid working on electrical equipment in wet or damp conditions. Water is a good conductor of electricity, and working in wet conditions increases the risk of electric shock. Seventhly, inspect equipment regularly. Inspect electrical equipment regularly for damage or wear. Replace any damage to worn equipment immediately. Eighthly, follow safe work practices. Follow safe work practices when working with electrical equipment. This includes avoiding contact with exposed wires, using proper grounding techniques, and never bypassing safety devices. Ninthly, be aware of hazards. Be aware of the potential hazards associated with working with electrical equipment. This includes electric shock, arc flash, and explosions. Tenthly, get training. Get proper training in electrical safety before working on any electrical equipment. This training should cover the hazards of electricity, safe work practices, and the use of personal protective equipment, abbreviated PPE. By following these electrical safety principles and practices, you can significantly reduce the risk of electrical injuries and fatalities. Overcurrent protection is a critical aspect of electrical safety that involves protecting electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can result from short circuits, overloads, or ground faults. Here are some key methods and devices used for overcurrent protection. Firstly, fuses. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when the current exceeds a predetermined level. Fuses are simple, inexpensive, and reliable, but they must be replaced after they have blown. Secondly, circuit breakers. Circuit breakers are overcurrent protection devices that automatically interrupt the circuit when an overcurrent is detected. Circuit breakers can be reset after they have tripped, making them more convenient than fuses. Thirdly, ground fault circuit interrupters, abbreviated GFCIs. Ground fault circuit interrupters, abbreviated GFCIs, are devices that protect against ground faults which occur when current leaks from a circuit to ground. GFCIs quickly interrupt the circuit when a ground fault is detected, preventing an electric shock. Fourthly, arc fault circuit interrupters, abbreviated SCIs. Arc fault circuit interrupters, abbreviated SCIs, are devices that protect against arc faults, which are dangerous electrical arcs that can cause fires. SCIs detect arc faults and quickly interrupt the circuit, preventing fires. Fifthly, overload relays. Overload relays are devices that protect motors and other equipment from overloads. Overload relays monitor the current flowing through the equipment and trip the circuit if the current exceeds a predetermined level for a certain period. Sixthly, surge protectors. Surge protectors are devices that protect against voltage surges, which are sudden increases in voltage that can damage electrical equipment. Surge protectors divert excess voltage away from the equipment, protecting it from damage. The National Electrical Code, abbreviated NEC, provides detailed requirements for overcurrent protection. These requirements specify the type and size of overcurrent protection devices that must be used in different types of electrical circuits and equipment. The selection of overcurrent protection devices should be based on the specific characteristics of the circuit or equipment being protected, including the voltage, current, and type of load. Overcurrent protection devices should be installed in readily accessible locations so that they can be easily inspected and tested. Regular inspection and testing of overcurrent protection devices are essential to ensure that they are functioning properly and providing adequate protection. By implementing proper overcurrent protection measures, you can significantly reduce the risk of electrical fires, equipment damage, and electric shock. A qualified electrician can help you select and install the appropriate overcurrent protection devices for your electrical system. The neutral conductor is a critical component of an electrical system that provides a return path for current to flow back to the source. It is typically grounded at the service entrance, which creates a reference point for the electrical system and helps to prevent voltage fluctuations. The neutral conductor is normally at or near 0 volts relative to ground. However, it can carry current under normal operating conditions, particularly in unbalanced three-phase systems or in circuits with nonlinear loads. In a balanced three-phase system, the currents in the three hot conductors should sum to 0 in the neutral conductor. However, if the loads are not evenly distributed among the three phases, the neutral conductor will carry some current. Nonlinear loads, such as electronic devices, can generate harmonic currents that flow in the neutral conductor. These harmonic currents can cause the neutral conductor to overheat and can also interfere with the operation of other electrical equipment. The National Electrical Code, abbreviated NEC, provides specific requirements for the sizing and installation of neutral conductors. These requirements are designed to ensure that the neutral conductor is able to safely carry the expected current and to prevent overheating. In some cases, the NEC requires that the neutral conductor be oversized to accommodate harmonic currents. It is important to properly size and install the neutral conductor to ensure the safe and reliable operation of the electrical system. A qualified electrician can help you determine the appropriate size and type of neutral conductor for your application. The grounding of the neutral conductor is also a critical safety measure. The neutral conductor is typically grounded at the service entrance, which creates a low impedance path for fault current to flow back to the source. This helps to quickly trip over current protection devices, such as circuit breakers or fuses, in the event of a fault, preventing electric shock and equipment damage. The grounding of the neutral conductor should be done in accordance with the National Electrical Code, abbreviated NEC, and other applicable standards. A qualified electrician can ensure that the neutral conductor is properly grounded and that the grounding system is functioning properly. Proper overcurrent protection, proper neutral conductor sizing and installation, and proper grounding are all essential elements of a safe and reliable electrical system.